Okay, so this is really strange. I just picked up on this at the end of last class. We're doing section 2.3. It's one day on the 23rd of 2023. Isn't that weird? Like, I feel like I should play the pick two. They have like pick 2, pick 3, pick 4 numbers. I think I'm going to play 23. But probably a lot of people would because it's the 23rd, so it's probably not a good payout. I'll think about it. Anyway, I'm just in my gambling head right now. We're going to talk about exponential functions today. So last week we started out doing arithmetic and geometric sequences, and then we talked about how arithmetic related to linear functions and geometric related to exponential functions. So today we're going straight in just to exponential functions, not a sequence, the actual just algebraic exponential function. So when we explore linear growth, you always have a constant rate of change, right? If you have an equation and slope, there's 23. There's a 23 again. That's so weird. Ooh, I got chilled. Okay, the slope tells us the output will increase by 2 each time the input increases by 1. So as we go up in our graph, we're going to change our slope 2 over 1 the whole way through. Okay, so it's constant. What happens with exponential functions is similar to geometric functions. We multiply by a ratio. Remember, it could be a fraction, it's getting smaller, a whole number, it's getting bigger. An exponential function is a function that can be written in this form. And we wrote them in this form pretty much on Friday. We just called it like, I put like an n there. Yeah, f of n equals a times b to the n, if you remember. Just those letters can be anything, and now in algebra we use x's, okay? Where b is a positive real number, and it can't be 1, and a can't be 0, it's a real number, blah, blah, blah. But here's the important stuff. The domain of these functions is all real numbers. You can plug any number that you want in for that x, positive, negative, 0. The base is called the growth factor or decay factor if it's less than 1, and I'll show you that. That's very easy. Show you that as we go. And the constant a is the initial value. Okay, that's confusing. So a is also your y-intercept. And that should connect to what we learned on Friday. If you remember over here, we used a sub 0 when we wrote it in this form, which is your y-intercept, the initial value. And in the word problems, remember, it was the number that we use before any time has gone by or any bounces of the ball. Okay? And so if b is greater than 1 versus less than 1, that's going to give us growth or decay. And I'll show you that. It's easier to explain in an example. Okay, so here we have an exponential function. We have 2 to the power of x. That power of x is what makes it exponential. And we're just going to plug and chug through this xy chart. We're given some x values to plug in. And then let's see what we get as our y values. Okay, so I'm going to start over in the positive numbers. Anything to the 0 power is 1, right? 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, okay? Now with the negatives, it's really important that you guys understand how to work with negatives without a calculator. Whenever you have a negative exponent, to make it positive, which is what you want, you would have it cross the fraction bar, right? So this is not a fraction right now, but you could make anything a fraction. So to make it a positive 2, it would just go to the bottom, and we would get 4 in the denominator. And there's nothing left on top, or you can always think of there being a 1 in front of everything. So 2 to the negative 2 is just 1/4. 2 to the negative 1 is 1/2. So whatever it would be positive, and then put it in the denominator. So 2 to the negative 3 would be 1/8, 1 over 8, and so on. All right, so let's just sketch this graph. Exponential functions always have lots of little fractions in them, and then the numbers get big and definitely more manageable to graph. So at 1, I'm at 2, at 2, I'm at 4, and at 3, I'm 8. Okay, and it makes this curvy graph that we saw graphed without a continuous curve on it in Friday's lesson. Remember, we recognize that as being geometric or exponential. But this is important. When we talk about it being a arithmetic or geometric function, the graph is called discrete. It's not continuous. It's just points. Notice we did not connect those points on Friday because the domain is just these x values. Just those. That's it. We don't connect them. It's not all the numbers in between. It doesn't go on forever and ever. But in an exponential function, these were just numbers we chose. We could have chosen anything because the domain is all real numbers. We just picked some numbers that are easy to plug in. And then we show that the domain is all real numbers by putting those arrows. One more thing I want you to add up to the top, if you want, exponential functions have an HA. You guys remember what my abbreviation HA is for? Horizontal asymptote of y equals 0 that dictates end behavior. So I'm going to explain that. Now, all the problems that we do today, they asymptote is y equals 0, and I don't think we go much further with it, but just like any other function, you guys, we could take these parent functions, the basic graph, and we can move them left and right and up and down and flip, and I think maybe we do later on, but for right now, it's just y equals 0, okay, and you'll see that here in a second. So here is our horizontal asymptote at y equals 0, okay? So let's just go ahead and fill that in. And what that means is our graph is going to get really, really close to it, but it won't cross it. It can't touch it. It can't go below it. That means that your y value can never be 0 numerically. Think about it. Take y equals 2x. I challenge you. Find a number that you can plug in for x that gives you a y of 0. What can I plug in there that gets me 0? It doesn't exist. Try any number you want. It's impossible to do mathematically, and that's why we show it as an asymptote on our graph. And you'll never get a negative number either. No matter what you plug in here, you will never get a 0 or a negative number there. So that keeps all of our points above 0 in this graph. Okay? So what would the range be if the domain is all real numbers, and after everything I just said, what would the range be? Anybody? 0 to infinity, right? 0 to infinity. Are we including 0? No. The whole point, right? It's an asymptote. So what that means is everything right above 0. The instant second you get above the 0, you are part of the range, but you can't be 0. Okay? Let's talk about this. This is end behavior written in limit notation. So let's talk about that again. That's not going away. As x approaches infinity or x approaches negative infinity. So remember, as our x goes to the right, that's positive infinity, right? As x goes to the right, the graph. And as it goes to the left, that's negative infinity. So it's basically saying, as x goes to the right, what is y approaching? Where is y heading? Up. For how long? To infinity, right? Hence that arrow, right? We go to the right and up forever as we go to the right, towards infinity. Now, as we go to the left, we can go to the left forever. And we are going down slightly, but will we ever reach negative infinity? No. What are we heading towards? 0. Yeah. So it's what you're approaching. I'm approaching 0. I will do that for the rest of negative eternity, but I will never, ever hit 0. I mean, our human brains can't really compute that the numbers can go on forever, but still never get to 0. But the numbers just get smaller and smaller and smaller and smaller. Because mathematically, it doesn't exist. We can never get a y equals 0 in that equation. It's not mathematically possible. Okay? All right. Intercepts. Yeah, we've got one, right? 0, 1. It's a y-intercept at 0, 1. No x-intercepts, obviously. In concavity, would you call that concave up or down? Up. Yeah, it's concave up. In your homework, they ask a few more questions. Is there any extrema? Remember what extrema is? What? Give me an example. Min or max. You are on fire today. 23 is your lucky number too, Levi. None. There's no min or max on these. Okay? And another question that gets asked, and I think I touched on it, is the graph continuous? And the answer is yes. It's not discrete like those points. If it's connected connected with a smooth curve. Like, you don't have to pick up your pen or pencil to graph it. There's not a hole in it. It is continuous. I can draw this graph forever and ever in both directions, and my pen never has to come off the paper. That's continuous. Okay? All right, next page. So the directions are kind of confusing. This is basically giving us some different types of functions. We're going to state the initial value, the base, and is it an exponential function, yes or no, and then why. Okay, so basically, remember when we were just talking about this is the equation that we're working with. A is your initial value or y-intercept. Okay, so if you want to write it again, or I think it was something in the printed out notes, it's your initial amount or your y-intercept. That's what A is. And B is your growth or decay factor. I didn't want to write it all out, but I will. Growth or decay factor. It's what we're multiplying by, okay? In the chart, in the XY chart. Okay, so when I have to decide, so there's only two numbers in this, right? There's an A and a B. So B has to be the number that has the power. That's what it says. So B is my base, right? Base with a power of X. So what would my initial value be if I don't have one? 1. So it's just like any other time when 1 is a value, we don't write it, right? 1 in front of an X, we don't write it. X being, or 1 being an exponent, we don't write a 1. If they don't see it, we know it's a 1. So same situation. So our y-intercept on this one would be 1. We graphed it. And yes, this is exponential. It's in the form of an exponential, which is a times b to the x. X is a positive x and it's a power. That's what makes it exponential. Now this one, 4 would be our initial value, and x is the base. This is not an exponential function. Notice we have an actual value as our power, not an x. And if you remember what I was just saying about the negative exponents putting you in the denominator, this is really y equals 4 over x to the third. That x to the negative 3, because the x has a negative exponent, would move down to the bottom. And that's actually what we did last unit. That's a rational function. We have a poly on top and a poly on the bottom, so it's not exponential. Now, this letter E that you see here and here, let me talk about the letter E. You guys know what pi means, right? Pi is that symbol we all know about, and it equals 3.14, and then go out in the hallway and see the rest of them, right? So pi is a placeholder for that very special number that we use in geometry and trig, which is the circumference of a circle divided by the diameter of a circle. And we have a button for that on our calculator. It's above the exponent key, okay? So there's my pi symbol, and of course I can hit enter and I can see what it equals. So pi is kind of like a symbol, but it represents a number that we know, okay? But it's easier to write that symbol than blah, 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 okay? E is the same thing. E is a variable, a symbol, E, lowercase e. Its button is above the division symbol. So you can put it on your screen, but you can also know what the value is. It's similar to pi. It has a known value. It's a placeholder for that known value. Whereas x is an unknown, right? We don't know what x is, or it's open. We can plug lots of numbers in. E is actually a number. So when you see this, first base, initial value 5, base of e, but this is not exponential because just like the one above it, if I wrote it, it would be e to the x in the denominator. Right? That's a rational function again. Okay? And same with this one. Initial value 3, base 4, but this is not exponential either because e is not x. It's a known value. And it's not like e, like when I said, oh, you can plug any letters in. Like I did f of n equals a times b to the n on Friday. Now I'm calling it an x. This is not the same kind of variable. Yes, it's a letter, but it's not unknown. It has an actual value. I could put that whole thing in my calculator. 3 times 4 to the power of e and it's going to give me an actual answer. It's a constant. There's no letters involved at all. It's actually 129 point blah, blah, blah. So, I'll just write this. Okay, so there's no x as the power. So in the homework, there's going to be some questions where you have to identify like what's going on with it by some of those things I just said. Okay, without a calculator, there's a hint that there's probably going to be some arithmetic we have to do without a calculator on our test, on the exam, so let's practice that. We get a little rusty with it because we do such high-level math that we don't have time to actually like do division. We just let the calculator do it for us. But there are times that we have to know how to do some of that arithmetic again, like 2 plus 1 without a calculator. Okay, 2 plus 1 is 3, of course, and then we have to do, remember, not 6 times 3 first, 3 to the power of 3 first. So 3 times 3 is 9, and 9 times 3 is 27. So when I plug in a 2, what do I get? Remember this kind of math? Oh my gosh, how long has it been since you had to do this? 62. So 6 times 27. So when my input is 2, my output is 162. Okay. Same thing here. I'm going to teach you something. Actually, I found out last period that you have probably learned it. Again, I'm sorry if you had Miss Shackton, you learned it. I don't know about your other teachers. But I'm going to show you, teach you or reteach you how to handle a fraction exponent. It's really easy. But if you have a fraction exponent, I'm sorry, that's so loud. If you have a fraction exponent, we rewrite that exponent as a radical. So what you do is you make a radical and you put that base in there. And Ms. Shackton used the, someone said top dog gets the house. I don't know if that makes sense to you. That's not what I do, but I'll allow whatever you want. So I say, so if you make a fraction with your hand, right over left, like 1/3, I say right over left, hug somebody. So that tells you how to open your hand. So you can never hug somebody like this, right? So it's right over left, hug somebody. So my right hand is the numerator. My left hand is the denominator, and we just put them in those places. So 1/3, 1 goes over here, 2 goes over here. However you want to do it, maybe you don't need a trick because you already memorized it, just what I was telling you. But that would be 8 to the first power is 8, and the cube root of 8 is 2. Okay. Another really common one is a power of 1/2. Think about that. Make your radical. 4 goes inside, and that's a 1 and a 2 there. So it's the square root of 4, which is 2. Okay. So that's all that is. And the calculator would do that for you, but this is a without a calculator problem. So -5 times 2. So when x is 1/3, y is -10. Okay. All right, given some info, we need to write an equation in a times b to the x form, okay? So if we are given this first piece of information, the value of g at x is 0, okay? X is 0, y is 3. Okay, we know that that's a y-intercept, right? And the output value of g doubles at every 1 unit increase. So as this goes up by 1, we double over here. So that's multiplying by 2, right? So we can just double. And whenever you have a number here that doubles, think of your XY chart. We're multiplying by 2 the whole way. We were calling it an R with a geometric sequence. In this case, it's a B. If we were adding the same number as we went, if it was like +3, +3, +3, that would be linear. Okay, it would be a line. So we know that this is going to be in the form of A times B to the X. A is our y-intercept, which is 3. B is our growth factor in this case, which is 2. So our answer is a couple more on the next page. We're going to do example 5 and 6, not 7. Your y-intercept. When x is 0, that's your y-intercept, and a is your y-intercept, your initial value. Same thing for these. Same exact thing. So as you look at your chart, as we go left to right, don't look at those two because those are not really friendly. But you can see here and here, we're multiplying by 2, right? If you couldn't tell, you could go backwards, 12 divided by 6, 6 divided by 3. So we're multiplying by 2. So we know that we have a growth factor of 2, 23. What is our A value? 3. It's the same problem as we just did. And it's 2s and 3s again. Wow. I feel like the universe is trying to tell us something, guys. I don't know what that something is yet. Okay, look at this one. As we go left to right, what's happening? Dividing by 2, which means what? Multiplying by 1/2, okay? So be careful, because you could think, oh, I'm dividing by 2, so my B value is 2, but it's not. It's what are we multiplying by? We're getting smaller. Our answer, our B value has to be less than 1. And our A value would be 5. So 2 is showing growth. That's a growth factor. And 1/2 is showing decay. That's a decay factor. So if you're going up, getting bigger, you're growing. If you're getting smaller, you're decaying. Easy. All right, last ones. Quick sketch of the graph for directions make no sense. We're given an exponential function. A is greater than 0. B is greater than 1. Right? So we have a y-intercept of 3, a B value of 2. Our graph is increasing. That's what that means, because the B has a growth factor. Right? This is growing. It's getting bigger as we go left to right in the chart or on the graph. So let's just sketch that. So we know we have a y-intercept at 0, 3, right? The A value. And if we're increasing, we would look something like that. Just a sketch. We don't need an XY chart or anything. We also know we have an asymptote at y equals 0. Be careful not just to write 0. It's a horizontal asymptote at y equals 0. Kind of skipping around here. What's our domain? Yeah. What's our range? 0 to positive infinity, not including the 0. And then there's that end behavior business. As x approaches infinity is the first one. So that means to the right. We are going up forever, right? As we go to the right, we go up forever. As we go to the left, we're approaching 0. Last one, A is greater than 0, A is 5, right? That's my y-intercept. B is less than 1, so our function is decreasing left to right. And the base B is its decay factor, because it's less than 1. That tells us it's getting smaller. Okay? So there's my y-intercept of 0, 5. I'm not good at graphing these this way. But we're going the other direction, right? We're decreasing as we go left to right. Something like that. Asymptote's not going to change. Domain and range, not going to change. Still all real numbers for our domain. Still staying above 0 for our range. The end behavior is changing now, right? As we go to the right, so as x goes to the right, what are we approaching? No, to the right it's 0. Look, it's not going to be able to cross this. So when we go to the right, 0. To the left, it's going to infinity. I just didn't hear you when I said what.
Yeah, no, I didn't.
Oh. And that's it. Good? Not bad. All right, there's only one practice set, so go to it. And I didn't have you guys do number 23. I messed with stuff.
And there's only 22 copies.
That's 16. Oh, there's a total. Okay. Well, then. All right, guys, and the directions say hundredth. Actually, it should be thousand. 3 decimal places. Okay. So have that written down, and I'll work my magic to make it fit up here somehow. You're not doing it.
No way. To be extra credit, but only for second and third period.
Why second?
Because, yeah.
Oh.
Yeah. We're going all in.
I did not catch on to that.
But don't.
I will say it.